Well, here's a joke. If you open the dictionary and look up recursion, the definition says see recursion. You get it? Which causes you to go back to the entry for the word recursion. Tells you to see recursion. Nerd humor. So what is recursion mathematically? Recursion is a process where there's a rule, some kind of procedure, or as Nina put it, a transformative rule, which involves taking some input, performing the rule on that input, and out comes some transformed expression or a picture or a value, call it the output. Recursion then takes that output, and the output becomes the new input. And then we apply the same exact rule on that. And it's an infinite loop. Just keeps going on and on, each loop being a iteration. Each iteration needing the previous iteration. And none of this can begin, of course, unless you have that very first input that we call the seed. Number two, an important observation we made about recursion is that if you use the exact same rule but different seeds, you can have radically different behavior. In other words, if on one hand we had a seed of 1, the iterations could be something like this. First iteration 13, second iteration 50, third iteration 4,568, fourth iteration 26,400,000. So the seed of 1 could have behavior where the successive iterations explode very quickly. On the other hand, using the exact same rule, but starting off with a different seed, maybe 2, it's possible maybe that the first iteration is -3, and the second iteration is positive 5.4, and the third iteration is -2, and the fourth iteration is positive 5.1. It could be that no matter how many iterations we look at, all of these values stay within, I don't know, within 10 units of 0. And they never explode the way the other example did. It could be that another seed quickly converges to values like 0.9, 0.99, 0.999. It might be converging to 1. So big idea here, using the same rule, but different seeds, you can observe radically different behavior in the orbit of that seed and what happens with each successive iteration. They might explode, they might come to toggle between 2 finite and relatively small numbers, or they might converge toward 1 limiting value, like this series that seems to be converging toward 1 maybe. Here's a very short example of what we're talking about. So using this rule, remember the notation, the n plus 1 is a subscript, an n. Really all it means is to find the next term, to use the previous term. So if the seed is 1, then to find the next term, you'll use the previous term, which was 1. So 1 squared minus 3 is negative 2. To find the next term, we'll use the previous term. Negative 2 squared is 4 minus 3, which is 1. To find the next term, we'll use the previous term, which is 1. Previous term squared minus 3 is 1 minus 3, which is negative 2. And this pattern is going to continue. Starting with a seed of 1, first iteration was negative 2, the next iteration was 1. The next iteration is negative 2, the next iteration will be 1 again. What about this seed? What if x sub 0, the seed value, is 2, positive 2? In the first iteration, we'll use the previous value. It'll square it and subtract 3, which is 4 minus 3, which is 1. And to get the second iteration, we'll have to use the previous one, which is 1. 1 squared minus 3 is negative 2. And we're back into that pattern again. So 2 different seeds, and they sort of yielded the same pattern. Is there another seed we could use that would generate a completely different pattern? Yeah, there is. Let's take a look at one of those. Just consider a seed like, oh, I don't know, maybe the seed 3. What would the first iteration be? To get this term, this next term here, we'll have to use the previous term. Previous term squared minus 3 is 6. To get the next term, we'll take the previous term, square it, and subtract 3, and that's 33. So this is radically different from the last 2 seeds. The next iteration is going to be very large because we have to take the previous term, which is 33, square it, and subtract 3. And that's a big number. 1086. By the next iteration, we'll be well over 1 million. That concludes number 3.